First up is the Brymen. This is the BM869s. This meter cost about $230 US. We'll hook it up to our original generator. Let's just see if it can withstand this. Okay, that's it. Let's test it out and we'll see if it's still functional. I hate to say it, but the Brymen does not survive. It's in resistance mode now. It's reading about 1.1239k ohms with an open. When it's looking at resistance mode, it appears that the drive comes down this leg and the return path is up this direction here. I can see plenty of drive strength here, and you can see it definitely is loading down as it works its way up through the chain here. So I've got replacement transistors. These are marked in R1P. That's a 2N2222. I'll go ahead and replace these and we'll see if the meter's corrected. Okay, these are my two new transistors installed. So let's just try it out in ohms mode now. Hey, so no more 1K resistor. Hello again. So if you've been following my videos, you know that Brymen had donated a few meters to me to do some destructive tests on, and one of them happened to be a second BM869s. And the reason that I asked them to provide this particular meter is I wanted to life cycle the rotary switch on it. So this meter has been tested and then I went fishing with it, but it is 100% functional. You can see it's still working just fine. So way back when I first bought my BM869s, I ran this meter through the same transient test that I ran all the meters through. And this particular meter survived everything that this transient generator could put out. At the time I didn't have a way to reprogram my higher voltage transient generator. Basically, if you may remember, I was rebuilding that transient on every single event. So after I finished testing this meter using this transient generator, I had gone ahead and attached it to the high voltage transient generator, and that generator was strapped the same way that I tested the Fluke 101, and that was 13,000 volts with a 100 microsecond full width half height. And unfortunately it damaged this meter. I was able to go in and repair it, had some interesting discussions with Brymen about it. Anyway, I thought what I would do with this meter is repeat those tests. So I'm not going to go through and rerun all the tests with this generator, but it just so happens I'm looking at another Brymen meter, and we have it right here. And I just finished testing this meter, and I thought what I'd do, as long as this generator is all set up, it's running the highest voltage that it can put out, I'm going to repeat that same test on this BM869s, and then we'll functional test it, and assuming it passes, what I'm going to do is connect this to the high voltage transient generator, and we're going to walk it up through and we're going to find out exactly where this meter fails at. This is looking at the waveform. Again, sorry about the glare. You can see it's 2 volts per division and 100 microseconds per division. And you can see it's 3 divisions up, or basically 6,000 volts. It's just shy of that, and 100 microsecond full width half height. So again, that's a pretty big transient. I haven't had a Brymen that failed this test yet. Certainly a lot of other ones have. So let's go ahead and get started. Alright, so again, this transient generator will put out about 5,800 volts max, and that's a 100 microsecond full width half height with a 2 ohm source impedance. We're going to be applying both positive and negative transients with each mode of the meter, and we're going to repeat that 5 times. Here we go. Camera batteries just died. Alright, I'm not sure how many transients we made it through. I'll just give it another 5. Alright, that's it. I'll go through and functional test it. We can just do a quick check here with our box. So this will be roughly 2.2, 2.3. This should be 2.5, and you can see we're at 60 hertz. This would be 30 hertz, that's just fine. This will be DC, should be 5 volts, that's just fine. Of course, I got the polarity inverted. There you go, there's 5 volts. This should be roughly 60-ish volts. That's fine. And this should be 118, which is fine. Let's just try it with temperature. And this should be about 500 degrees. Let's just try it on the second channel. You can see it reads the same thing. We didn't zap that side, so I'm sure that that would have been fine. So this is with the leads open. Let's just try it with a 1 nanofarad capacitor. Looks good. This is a 0.1. That looks fine. This will be a 1 microfarad. Looks good. Here's 10. Looks good. This will be 100 microfarads. Looks good. This will be Diode Check. Here's with a short. And let's just try it with a single diode. And here's 2 in series. And this will be resistance mode. Of course, this is with the lead shorted. And let's just try, this will be a 0.5 ohm. Looks good. This will be 1 ohm. Here's a 50, 100, 1K, 10K, 100K, 1 meg, and this will be a 10 meg ohm. Let's just try our continuity test. Looks fine. Let's try looking at conductance. So this will be a 100 meg ohm resistor. Should read 10 nanosiemens. That looks fine. This will be a 1 giga ohm. It should read 1 nanosiemen. So yeah, it doesn't appear that we've done any damage to the meter. So this meter, just like this one here, look like they both survive the highest that this transient generator can put out. So I think the next thing I'd like to do is connect this to the original transient generator and run some higher voltage tests. So on the left here I have our high voltage transient generator. Looking at the scope, this is 100 microseconds per division, and it's also 2 kV per division, so you can see we're 3 divisions up, or 6,000 volts, and you can see the full width half height is roughly 50 microseconds. This is where we're going to start. Again, we'll be applying 5 transients, both positive and negative, with each mode of the meter, and then we'll go back and functional test it. Okay. Alright, let's go ahead and functional test it. Alright, so the BM869s survived that transient just fine. You can see I've changed our transient generator. This is still 2,000 volts per division, so you can see we're now 4 divisions up, or 8,000 volts peak. And this is with a 50 microsecond full width half height and a 2 ohm source impedance. And we'll be applying 5 transients, both positive and negative, with each mode of the meter. Let me just scooch the... There we go. Alright. See what it still looks like. Not much difference with the meter. Alright, the battery's died in the camera. I think we had 3 transients. We've got 2 more to go. Okay, that's it. That was 8,000 volts. Let's go ahead and functional test it. Alright, so the BM869s passed the functional test just fine. You can see I've restrapped our generator again. This is now putting out 10,000 volts. You can see it's 5 divisions up. Zoom in here a little bit. It's 50 microseconds per division. Halfway point is about 50 microseconds full width half height. Again, we'll be applying 5 transients, both positive and negative, with each mode of the meter. Alright, here we go. 10,000 volts. It's the first transient. Looks fine. That was our last transient. Alright, let's have a look at this thing functionally. Again, that was 10,000 volts. I'm probably getting close to where the meter is going to fail at. Should be roughly 2.2, yeah. It should be 2.5. That's at 60 hertz. This should be 2.5 as well. This will be at 30 hertz. That's fine. 15, 120. Should be roughly 70 volts. That's fine. This should be 60 volts. That's fine. Should be 115 millivolts. Yeah, we're definitely connected, right? Let's try it here. 115 millivolts? No, it's not. I think we've damaged it. Alright, let's try our temperature sensor. And this should be roughly 500 degrees. Nope. Let's clamp down. Let's try capacitance mode. Oh. So there's diode check. This is with a single diode. There's 2, that's fine. And let's try capacitance. Let's try resistance. Oh, 160 ohms. That's with an open. Yep, so we've damaged it at 10,000 volts. Alright, let's go ahead and pull the meter down. We'll see if we can figure out what went wrong with it. A little bit of Brymen on Brymen action. Alright, the last time we blew one of these up, I think it was these 2 transistors right here, and those were a 2N2222. So, let's just have a look. Yeah, that one is appearing to leak. Let's check this one. Yeah. Yep. I think it's these same transistors again. So that one looks fine. That one's fine. That one is fine. Yeah. Let's check these 2 while we're at it. That one's fine, and that one is fine. So again, I suspect it's this one and this one, just like before. They changed the part. Originally, when I damaged this meter here, these were marked RIP. They are now marked a VLR. We'll have to look that up and make sure it's the same part. Before we look them up, we'll just go ahead and pull them out of there. Just check them real quick. Yeah. See that? We're measuring 0.43 both directions. Let's check the other one. 0.40 and 0.39, yeah. And these are both bad. Alright, so I looked these up under the microscope and they're not marked like that at all. So they are 2N222. So no problem. We've got a couple of new ones here we're going to put in. It'll power up, no problems. I expect that's going to be the only thing we're going to find wrong with this thing. I'll just go ahead and button it back up. Alright, so an open, looks good. So we'll try this in conductance. This will be 100 mega ohm, so this should be 10 nanosiemens. Looks dead on. I think that's all that's going to be wrong with this thing. Let's just try it with a 1 giga ohm. Again, this should be 1 nanosiemen. Let's try it in resistance. Reads an open now. Let's try 100 meg or 100k, 100 ohms. So that looks fine. This will be a 10k. I'm sure this is all fine. This will be 10 meg. Looks good. Continuity test. That's fine. Capacitance mode. Again, this will be a 150 picofarads. It looks good. 0.16. This will be a nanofarad. Looks good. And 0.1 microfarads. Looks fine. Let's try it in diode check mode. Here's a single diode. Looks good. Here's 2. That looks fine. Let's try temperature. Again, this should be roughly 500 degrees Celsius. Looks good. And again, we should be able to vary this. Should be roughly room temp. Yep, and a little over 1,000. Looks fine. The millivolts did not work before. Let's try this. It should be 115, 118, yep. 60 hertz, that's correct. Should see the same thing here, 118. Yep, that's fine. So yeah, it looks like that's all that we damaged with the meter. Alright, so this is looking at all the data I've collected for the meters to date. You can see I have 2 rows for the Brymen BM869s. The top one is the original, and this lower green one is the one we just ran. So again, I started my testing at the high end of the smaller transient generator. So this is at 5.9 kV, and the meter passed that test just fine. We went to 6 kV and it passed, and then 8 kV and it passed, and it failed at 10 kV. So the original meter, what had happened is I ran it all the way up on the low transient generator, and then again the high voltage transient generator was not programmable back then. So I just ran the unit on the 13 kV 100 microsecond full width half height, and the meter was damaged. And again, both meters were damaged the same way. I lost the same set of transistors, so it does look like it repeats. So this is probably roughly what you would expect the meter to fail, at least on my test. But if we have a look at all the other meters where they failed, you can see very few make it up this high. As a matter of fact, the ones that have, we have the Fluke 107. We can see the Fluke 17B Plus had failed at this same level. The Fluke 101 has survived. The Fluke 115 has survived. This is the same voltage where the Hioki meter I've got started to break around the plastic. Looks like another meter that passed this test was the Brymen BM235. And the last one is our Gaussian Metrowatt M248B. That's certainly my most expensive handheld meter. In my original tests, again, the only meters that really ran up this high are the Fluke 101. So I don't think anybody could argue that Brymen knows how to make a very robust meter. Well, I think that's going to be it for this video. I hope you found it interesting. Till the next test. Later.